Hi, this is Professor Fernandez, and this is video 2 in lesson 15. So we're continuing our discussion here of applied optimization problems, and I'm going to work through applied example 4.24 from Calculus Simplified. So there's a couple of things to mention here before I start going through the example. The first one is that there are a couple of videos that I recommend you take a look at if you haven't already, or if you're comfortable with optimization theory and to some extent have done an optimization problem in calculus. You may not need to check these out, but video 15.1 is the video right before this one in this lesson where I work through one optimization problem. You might want to take a look at that just to get a sense of where we're going to head in this video. Video 14.2 also does an optimization problem, but there's no real-world context there. So that will help you review the theory. So the theory of optimization in terms of optimizing a continuous function defined on a closed interval is kind of what this box 4.4 here is all about. So I talked a lot more about that, as I said in the video 15.1. In this video, I'm going to talk more about this box up here. You can see that this one is longer. It's got the same sort of title. I'm just going to zoom in here. How to solve an optimization problem with a closed interval. It's longer because, as you'll see in this example on the left, in most cases when you're dealing with optimization problems in real-world contexts, if it's a medium to difficult problem, you won't be given the function that you need to optimize. So that's step number 2 here, looking for keywords or clues about what that function is. That function is called the objective function. You might also have to run into some constraints. That's something that we'll talk about when we get there. And then you might not know what the interval is that you need to consider. That's something else you might have to extract from the problem. So there's a lot more steps here because there's a lot more stuff to do in these medium to difficult optimization problems. So without further ado, let's go ahead and look at this example and start working on some of those steps. So it says, consider the cylindrical can of soda pictured in figure 4.14. So that's actually this diagram that I drew in here. It says, if the can is made of aluminum and is to hold 21.6 cubic inches of volume, about 12 fluid ounces, what dimensions minimize the amount of aluminum used to build the can? So 2 things you could tell right away from this prompt. Number 1 is we are looking for the absolute minimum of something, and we're going to have to figure out how to quantify the amount of aluminum used to build the can. Okay, we'll get to that in a minute, but the point is we're looking for the minimum. And then number 2, we're told that the can has to hold about 21.65 cubic inches of volume. Great. So as you get more comfortable with these optimization problems, you'll be able to recognize what these pieces of information actually mean. Again, this number 1 and the squiggle here that I've drawn is going to tell us the objective function. This number 2 is going to tell us the constraint in this problem. So the first thing that I want to do, I'm going to follow, go to the right and follow my box procedure here. Again, you don't have to follow this procedure, but it's nice to have a procedure to lean on. As you get more comfortable with optimization problems, you might find a procedure that works for you, but if this is one of the first times you're doing it, it's nice to have a set number of steps that you can follow. So let's look at this number 1 here. If possible, draw a diagram. Okay, so diagram is here, and identify the variables in the problem. Great, so this diagram has kind of identified them for us, right? We are building a can, a cylindrical can, and a cylinder has a certain radius, has a certain height. There we go. So I've drawn a diagram and I've identified some variables. Number 2, look for keywords. For clues about the objective function. So we did that over here. So that's kind of the squiggly here. So I want to minimize the amount of aluminum used to build the can. Okay. So I have to quantify amount of aluminum. So if we go back to our picture, right, this is one of the nice things about drawing a picture, we are building a can. So if you think of a regular soda can you might buy at a grocery store or something, and think about how it's built, it's got the side part, so it's got this stuff, what's over here, and then it's got a lid, and then it's got a bottom. So the amount of aluminum used is a question of the area, right? How much aluminum here, how much aluminum here, and then how much aluminum on the sides. So we're going to take this cylinder that we have and we are going to unwrap it. So if I unwrap the cylinder, I get this, if I start unwrapping it, this is kind of what it would look like, right? There's my unwrapping of the cylinder. And then I continue unwrapping it and it looks more like this. There we go. Okay. And then I finally unwrap it and I just get one sheet. Okay. Now the area of this sheet, right? How would I figure this out? Well, remember that we said that the radius here is r and the height is h, right? The height continues to be h, and the height continues to be h, and the height continues to be h. But now what is this distance? Well, this distance came from the distance all the way around the bottom, right? The distance all the way around the bottom. So in other words, that distance is the circumference of the cylinder. So this distance is 2 pi r because that's the circumference of a circle of radius r. So in terms of the area, right, I can now say that the area a sub s, let's call this area of the side of the cylinder, equals 2 pi r times h, right? This times this, just a regular area of a rectangle. So 2 pi r h. Great. Now, this is not how you make, this would be a terrible can of soda. Just an aluminum sheet, put into a cylinder shape, right, with no top and no bottom. That obviously cannot hold anything, can't hold liquid, and can't hold soda. So we need also to add the area of the top. That's the area of a circle of radius r, right, because that's the same radius here we're using for the cylinder. So circle of radius r is area is pi r squared. And then that's also the same, it's the same area on the top as it is on the bottom. So the area of the bottom is also pi r squared. So now I have 3 contributions to my total area for the cylinder with a top, with a bottom, and with the sides. So I'm going to add those up, and that will make my objective function. That is how we are going to quantify the amount of aluminum used to build this can. Okay, so I'm going to speed things up a little bit here with erasing. And then we say, great. So the amount of aluminum, we're going to call that S for surface area, equals 2 pi r squared, area of the top and the area of the bottom, plus 2 pi rh, the area of the sides of the can, of the side of the can. And then r and h here are the variables that we've identified. It seems like the units that they want us to use are inches. So we're going to think of r and h as having units of inches. Okay, so we have quantified our objective function, right? So great, did that. So we're down to step 3 here. Identify the constraints. So I say here, this might, a tip-off might say at most or at least or exactly this much. This is where you can see that if the can is made of aluminum and is to hold, is to hold is kind of the operative phrase here. That's a constraint. So the can that we're creating here, we're designing, we're building, has to have a capacity of 21.65 cubic inches of volume. So volume, right? So we're dealing with a cylinder. What's the volume of a cylinder? What's the area of the base times the height? And that needs to be equal to 21.65. So that's why this is called a constraint, because it literally places a constraint on the variables r and h. R and h cannot be whatever numbers they want, right? They have to be related in this specific way. So at this point you have a choice, right? One of the ways that you want to incorporate constraints in your optimization problem solving procedure is to solve for one of the variables and then eliminate that variable from the objective function. Because right now, notice I didn't put here s of r because it is not a single variable function. At this point, actually, it's s of r comma h. It's a multivariable function, right? But this class is a single variable calculus class, so we want to eliminate one of these variables, r or h. We do that by means of the constraint. So at this point, you have a choice. You can solve for r or you can solve for h. Which one should you do? Well, I will point out that solving for r will throw you into finding a square root and a plus or minus. You'll quickly realize that R is a radius, it can't be negative. But the larger point there is that it seems a little easier to solve for h, right? So I don't have to take a square root. I just divide by this part. So I'm going to do that. H is 21.65 over pi r squared. In other words, the takeaway is remove the variable that's easiest to remove, right? And the algebra will give you some information about what that variable is, which variable that is. Okay, so I'm going to take this h and then substitute it here. It's the only place h occurs. Once I do that, I do in fact get rid of h, so therefore I can write down my function as a function of just one variable, r. 2 pi r squared stays, there's no h there. And then 2 pi r h, well, I'm putting this down here. 21.65 divided by pi r squared. Okay. Simplifying that a little bit gets me to 2 pi r squared plus 43.3, just doing out some of the math here, divided by r. What happened to the pi's? Well, this pi canceled with that one. One of these r's canceled with that one. And then I multiply the 2 times 21.65 to get 43.3. I'm always very cautious about canceling variables, right? I want to think a little bit about whether r can be equal to 0, but it can't. If r is equal to 0 up here in the constraints, there's no way the volume will be 21.65 cubic inches, which is a constraint in the problem. So we are safe in canceling r's because r cannot be 0. Okay, so now I have the objective function, right? I have the actual objective function. The next thing I need, let's go back to our box procedure here. We identified the constraints. Figure out the interval, right? And you might want to use the constraints. They might help. What do I mean by the interval? Well, when you want to optimize a function, it's nice if you know the smallest and largest values that you could potentially have to consider, right? So what is the smallest r value? And what is the largest r value? Okay, so we just talked about the fact that r cannot be 0. How about, I don't know, 0.1, or how about 0.2? What is the largest or smallest r values that you can have? Sometimes the prompt gives you this information. Sometimes, like I said earlier, you want to, in the earlier video, 15.1, you want to get some sense of the context, real-world context of the problem. If you're a soda manufacturer, right, I think the thinnest soda cans I've seen ever at a grocery store, maybe something like this. And that's exaggerating, right? So there's a certain R value beyond which the manufacturer is just not, you will never see a soda can that looks like this. So we're talking about R here in inches, so you can safely assume some small value of R in inches that is probably going to be as small as the manufacturer is going to be wanting to go. Again, I'm doing this in this particular problem because we don't have any other information about the smallest R value. So we're using the context here, the fact that we're building a soda can, to give us some information. Why 0.5? Not really any particular reason, right? It could have been 0.25, could have been 0.125, 0.1, just some small R value beyond which you think, a manufacturer is just not going to make a soda can of radius 0.000004 inches, for example. The largest R value, however, this is something that we can get from the constraint. All right, so I'm going to go back here to the constraint. I erased the R, so I'll put it back in. And here's the thing, right? If I go ahead and solve for H here, so if I go ahead and solve for, for H, this is what we did before. I want to figure out what is the largest R value. Well, I can kind of get some information from this constraint. So suppose, for example, remember H is in inches. I want a soda can. I can think the other way. I was drawing a lot of pictures about this, talking about the radius. What if I go to a grocery store? You think you'll ever see a soda can that looks like that? That's a very, very strange soda can. And it would take up a lot of space on the shelves, so manufacturers and grocery stores won't like that. In other words, you don't want a very, very small height for your cylindrical soda can, for the same reason you don't want a very, very small radius for your cylindrical soda can. So the height we're thinking is not going to be very small either. So you might want to set kind of a lower bound. You might say, well, I want the height to be at least 1 inch, for example, right? So even that, again, is going to result in a can that looks not too different from that. But again, you want to be a little generous. So let's say you say the height is at least 1 inch. Again, you could pick a number, 2 or 3 inches. Then what does that imply about the radius? Well, the height has to equal 21.65 divided by pi r squared. So if the height is bigger than or equal to 1 inch, right, then now we have an inequality, pi r squared less than or equal to 21.65, and we can solve for what the largest radius would be. R has to be less than or equal to the square root of 21.65 divided by pi. This is about something like 2.63 if you work it out. So let's be a little generous here, and let's say R should be no larger than 3. Okay. So you can see, again, why optimization problems that don't have a lot of explicitly given information, they give you the function, they give you the interval, take a little longer and a little more complicated. There's a lot more stuff you have to think about doing, right? But still, the procedure is clear, right? We have found our objective function, we did that, and we just found our interval, we did that. So now I'm going to go back to our box and continue with that procedure. It's been working out well for us. We use the constraints, right, to figure out the interval. We also use the context. Next one, number 5. If the interval is closed and the objective function continuous, use box 4.4 to find the absolute max or min. Great. So let's do a check here. The function that we have obtained is a continuous function on this interval. That's important to note. It is not a continuous function because it's not defined at r equals 0, but on the interval of interest, it is a continuous function. And the interval that we're looking at is a closed interval, so double check. So now we can go through and find the absolute max and min using this box 4.4. Again, this is something that I talked about in video 15.1 and also 14.2. So I'm just going to go ahead and go through the procedure there to find our absolute max, our absolute min, because we are minimizing the amount of aluminum. Okay, so that procedure basically said, take your function, which is, I erased here the 43.3, which is this one. Take your function, and then find the critical numbers associated with that. So that's the first step of the procedure. I'm just moving everything up, making some more space for myself. So number 1, right, at this point we're kind of in math land, right? We have a function, we have a closed interval, we're going to find the critical numbers. So now we can forget about the context for the time being. So I'm going to find the derivative of this function. So that is over here, power rule. So 2r differentiates to r squared differentiates to 2r. 2 and 2 make 4, so that's 4 pi r. And then over here, this is 43.3 times r to the minus 1. Also a power rule. So r to the minus 1 differentiates to minus r to the minus 2. So this is our derivative. And again, we're finding the critical numbers here. So we want to ask, are there any points where, any r values where this is equal to 0, or where it does not exist? There is, because if we have an r in the denominator, an r value at which the derivative does not exist, right? That's r equals 0. However, that is not inside the interval. So we reject it from consideration. So let's look at the other part, the so-called stationary points. Are there any values for which this is equal to 0? So now we want to solve 4 pi r equals 43.3 over r squared. And if we multiply here by r squared and we divide by 4 pi, we get to this. And then at this point, we can take the cube root. Take the cube root of 43.3 over 4 pi. And then we can calculate this out in terms of decimals. And this is about 1.5. Remember, r is measured in inches, so we get inches. This is the only critical number, therefore, right? We rejected this one, not in the interval. And 1.5 is indeed between 0.5 and 3. So this is the only critical number. Check. So now going back to our procedure, we have found the critical numbers. Now we want to calculate the critical values. We want to substitute those numbers into the function, get the y value, and then also calculate the y values at the endpoints. So that's step number 2. Okay, so I have found my r value, and I am going to go back and do step number 2 and calculate s of that r value, critical number. I also want to calculate s of the endpoints. The endpoints are 0.5 and also 3, and see what I get, right? The largest of these numbers is going to be my maximum, but I'm not looking for that. I'm looking for the minimum, so the smallest of these numbers is going to be my absolute minimum. Let's calculate the easier ones first. Let's see, where are we? Yeah, so this is our objective function up here, and I'm going to actually give you the decimal approximations of these rather than going through and calculating them in terms of their exact closed forms. And that's okay because we're just looking for the largest number here. So the first one gives you something close to 43, the second one close to 88, and the third one close to 71. Again, I'm looking at this function here, and I'm just substituting in these values for r, and then just working out what that ends up being. So if we were asked for the maximum, right, that would be right here. But we're not asked for that. We're asked for the minimum, so that is right here. So it just so happens that the absolute minimum happens to occur at the critical number that we found. The last part in our procedure, right, we have found the absolute minimum, but I put this step number 6 here because it's important. Make sure you finish by answering the question. Okay, so in other words, what was actually asked? Did we have to find the absolute minimum? Not really, right? Look at the question. It says, what dimensions minimize the amount of aluminum used to build the can? So we're asked for the dimensions, right? This is kind of what the manufacturer would want to know. Hey, I'm going to build a can that minimizes the amount of aluminum needed for holding 21.65 cubic inches of volume. What are the dimensions of the can that I need to build, right? So that's a very legitimate question from the manufacturer's point of view. Not tell me what the volume or tell me what the surface area, tell me the dimensions. So how do we do this? Well, we know that the minimum amount of aluminum used occurs when R equals the cube root of 43.3 divided by 4 pi. And again, we're measuring that in inches. So we know the radius. How do we find the height? Well, remember that we had the constraint. So our constraint was 21.65 divided by pi r squared. That came from the volume constraint. So all we have to do is take this r value and put it in there, and then figure out what that rounds out to be numerically. I'll save you the calculation here. It ends up being about 3 inches. Okay. So that makes sense with what we had said earlier in the problem. We were thinking a can should be at least 1 inch high, and that's how we got the radius to be at most 3, the right-hand side of our interval. So these are the dimensions, right? You probably wouldn't give the manufacturer this as the dimension, right? Because that is a little intimidating, and really it's not too far away from what we said the R value was numerically, which is 1.5. So you might say, hey, make the can 1.5 inches in radius and 3 inches high. And that will hold about your 21.65 cubic inches of volume and minimize the amount of aluminum used to build the can. Okay, this has taken a while, as all of these more tougher optimization problems take. So I will shorten what I say at the end of this video. Really, the takeaway is when you come upon an optimization problem, when you are not given a lot of information, you're not given here the objective function. We had to find that out ourselves. We're not given the constraints, right? We had to find that out ourselves. We weren't even told what the variables were, right? We had to figure that out. Then that's when this box 4.5 is really useful. I'll zoom in there. So again, you can pause this video, you can read through all the words that are in this box, or you can just, as I recommend, go back through the video and see me kind of checking each one of these steps off. It's not necessary for you to use this particular procedure as you do more of these problems and get comfortable with optimization. In real world context, you will come up with maybe your own procedure, right? But it is always useful to draw a diagram, identify your variables. If you have to determine your own objective function, right, that first step will help a lot. And then you might end up with a function that has more than one variable, like we did in this example. That's where you want to go back and look for a constraint. It must contain this much volume, right? It must happen in this much time, right? And once you have that constraint, at some point, like it happened for us, that will help you figure out the interval. At this point, if you have the objective function and you have the interval, you are set to apply the optimization theory. Hopefully the interval is closed and your objective function is nice enough to differentiate and apply all the critical numbers, critical points theory we have. And then the last step that's really important, make sure you answer the question, right? For all the work you've done, how disappointing would it be if you did all of this correctly and then you answered something other than what was asked? Your instructor, professor, teacher out there might not give you full credit because you might have, for example, in this problem, just stopped when you said, oh, s of cube root of whatever we found is approximately 43, and I'm done. Right? Whereas the question asked for what are the dimensions, which required a couple of extra steps. So that's why number 6 here is the last step. Make sure you finish by answering the question. Thanks for watching.